introduce this stuff. I'll make up an example real quick, and then we'll do the first couple on the practice for today. All right, so Tuesday we did the ideal gas law. Ideal gas law tells you all about a gas: pressure, volume, temperature, moles. So today we're going to do one different. We're going to get rid of moles, and we're just going to deal with pressure, volume, and temperature. So our formula today combines three different laws. Pressure, volume, and temperature all will change if you change another one. And I'll be honest with you, I don't remember which law is which because I got to look it up every time, and I'm not having you guys remember. But you have Charles' law, Boyle's law, and a guy named Gay-Lussac's law. If you put all those laws together, you get what's called the combined gas law, and it's how pressure changes with volume. So real quick, going to introduce those three laws and then combine them with the combined gas law. Okay, so we have pressure. Let me get that straight already because it was crooked Tuesday. We're not going to deal with it crooked this period. There it is. All right, so we got, first let's deal with pressure and volume. All right, so if I increase pressure on something, what happens to the volume? If I increase pressure on a gas, if I squeeze the gas, the volume gets lower, smaller. Okay, if you increase pressure on something, the volume gets lower. And it's kind of pretty straightforward, it makes sense. If you decrease pressure, it gets bigger. You let a balloon go, where does a helium-filled balloon go? Where does it go? It goes up. Okay, and as it goes up, what happens to pressure outside of the balloon? It gets lower. So what do you think the balloon's going to do as it goes up? Expand. Very good. Until it pops. Very, very good. Absolutely. So if you let a helium-filled balloon go up, it's going to go up. It's going to expand until it pops. Pretty straightforward deal. What about if you blow up a balloon in a space station and then put it outside of the window? Well, it'll freeze, but also that pressure will go from having an artificial pressure inside the space station to having zero pressure, and then pretty immediately that balloon is going to pop open because the volume is going to try to get so big so fast. Make sense? Okay, sure, yeah. All right, so that's pressure and volume. So let's keep on going. Let's look at pressure and temperature. And it's probably a little bit easier to think of changing the temperature than changing the pressure. So let's think about what happens when I raise the temperature on pressure. So for example, everybody knows this works for carbonated drinks. Okay, carbonated drinks are soda. You know, what's different between carbonated drinks and non-carbonated drinks?
No bubbles.
Yeah, they got bubbles in them. Those bubbles are what property of what state of matter?
Yes.
They're gases, exactly. And so you can look at what a carbonated drink does, and you can kind of understand what gas is going to do. So the volume can't change in a carbonated drink unless you do what? Well, how can you change the volume of a carbonated drink?
Take carbonation out of it.
Open it.
Yeah.
You with me? It's a sealed container. You can't change how much is inside of it unless it's open. Make sense? So what happens if I take a carbonated drink, a sealed can of Pepsi, and leave it in the back of my window on a hot sunny day?
That's not a good idea.
What's going to happen?
It goes up and explodes.
Very good. As temperature goes up, pressure goes up.
There was a Pepsi can that we left in the car in the sun, and I threw it outside, not realizing it exploded.
There you
It was
go.
kind of cool, but
As temperature goes up, pressure goes up. So we dealt with pressure and volume, we dealt with pressure and temperature. The only one left is volume and temperature. and you know this one because you know a hot air balloon. If I put heat into a gas and increase its temperature, what's going to happen to its volume? When you put heat into the balloon, what happens to it? It blows up. The volume goes up. Okay. Temperature increase, volume increase. So you have a direct relationship between pressure and temperature, a direct relationship between temperature and volume, and an indirect relationship between pressure and volume. Okay? If you combine all three of those together, you get the combined gas law. The 1 and 2 here represents before and after. So I have it written over here for my folks in the room. The 1 and 2 represent before and after. So the initial pressure, volume, and temperature, and the new pressure, volume, and temperature. Now, if anytime something is constant, you can just leave it out. So if temperature is constant, there's your formula. If pressure is constant, there's your formula. If volume is constant, there's your formula. So you can just leave it out if anything's constant, make solving the problem a little bit easier. So this is just showing you how things change in response to other things. Rock and roll. All right, so let's do an example. So let's say we have, let's say 30 liters of gas. At, how hot is it in the room? Let's say 20 degrees Celsius. And let's say it's under not much pressure. So let's say 60 kilopascals of pressure. Okay. I want to know how much gas we would have at standard temperature and pressure. Now, you don't have to remember what standard temperature and pressure are because they're on your yellow sheet. You can Google them, pretty simple. I don't need you to Google them right now because I'm going to tell you. The standard temperature and pressure are a way to keep things standard. The ideal gas law was all about standard temperature and pressure. We talked about that. 22.4 is all about standard temperature and pressure. Don't stress, but we'll get it straight here. Okay? So we got to just plug and play. Put all our numbers in and then solve what we don't know. Okay? So there's my initial numbers. Here's my final numbers. Okay? Simple enough. What's my P1? What's my initial pressure? 60. Okay? P1, V1, initial volume?
20 liters.
30.
Oh,
It's an ugly 30, but it's a 30. Initial temperature?
20 degrees Celsius.
But
We gotta turn to Kelvin.
the only time we use degrees Celsius is to plug it in to change it to Kelvin. The other units in this formula don't really matter. Remember, for PV equals nRT, I was big on units. For this one, I'm not big on units except for Kelvin.
So it's
If you're using temperature to do math, you gotta use Kelvin. So it's gonna be 273 plus 20, 293. Okay, so we got our left side filled out. Let's keep on rolling. New pressure. Anybody remember standard pressure in kilopascals from last week? We did it real quick. Sounds like a radio station. 101.3. Standard pressure is 101.3. Volume? No, I don't know. That's what I'm looking for. It wants to know the volume, and I probably should have written that. What's the volume at standard temperature and pressure? So my volume is what I'm looking for, so I'm gonna just put a V2. That's what I'm looking for. And standard temperature, I remember from that from last week or Tuesday. Standard temperature is 0 degrees Celsius, which is, it is 32 degrees Fahrenheit, but I don't care about Fahrenheit. 0 plus 273. That's a tough math problem.
Oh, yeah.
273. All right. The only thing left for me to do is some algebra. Okay. Let me make this algebra easy for you though. What I would do with this algebra is cross multiply and divide. Now you can do it any way you want to. You can do it step by step. You can say this times this, enter, divided by this, enter, times that, enter, divided by that, enter. You could do it that way. I prefer to do it all in one step, cross multiply and divide. So what I'm gonna do is I'm gonna multiply all of this stuff, and then I'm gonna divide it by all of that stuff. So that's a cross multiply and divide. Divide by where your unknown is. Okay, so I'm gonna say, this is what I would type in the calculator. Start your parentheses, 60 times 30 times 273. Close your parentheses, divided by, start your parentheses, 101.3 times 293. And if you do it that way, you do it all in one step. You don't have to, you let the algebra do itself. Cool. Everybody practice the calculator. See if you got the same thing Josh got. Only 6 problems today. A lot of meters cubed and decimeters cubed today on your homework or on your practice. These two things are the same as liters and milliliters. Actually, it's the other way around. So I don't care what the units are as long as they stay the same. So don't let decimeters cubed and meters cubed screw you up. What we got?
I got 1.65.
Sounds good to me. 1.65. Any disagreement? Any problems? Got agreement?
Mine came up 16.5.
They said 16.5.
I said
Leave out a 0 somewhere. Double check your math. Hit up and double check your math.
I'm happy.
You're fine. Josh says he agrees with Josh, right?
All right.
Oh, no. He's agreeing with Ashley. Styron? What are we on, bud? Talk to him. You type it in?
No, not yet.
Well, type it in. Matthew, type it in yet? Come on, man.
I'm agreeing with Josh.
Tanila? 16.5. I got 3 16.5s. Double check your math. Are you sure you're not in scientific notation? Is it times 10 to the something?
He multiplied it first, and then when he got that answer, he divided it by.
Did he use parentheses?
I got 16.5.
Yeah, I think you might be in scientific notation, Josh. Look, it might be 1.65 times. Ooh, dang. 1.65 times 10 to the 1. Double check.
What?
Yeah, more is already cleared.
I think 16.5 sounds better. 16.5 what? What was I looking for? I was looking for volume, 16.5 liters. Whatever you get, whatever the question gives you is what comes out. All right, I got 6 questions. Y'all cool with doing the first 2?
Yes.
All right, let's do the first 2 just like we've been doing, and now I'll set you free. All right, looking at number 1. Everybody looking at number 1. I see a bunch of computers up, good. So let's just roll. I'm gonna read it, and then I'm gonna ask you to tell me what to put where. There's my formula right there, if you need to refer to it. Pressure of a gas changes from 120 kilopascals to 50 kilopascals. The volume changes from 45 to 40. Its initial temperature is 81. What is the final temperature? All right. So now give me a P1. 120. Yeah, you got me. Come on. You got a question in front of you, don't you? Okay, so give me a V1. What's your initial volume? Read the question. It says the volume changes from. Okay, it's what number are you on?
We on 2.
We're on 1, boss.
Oh,
What's your initial volume?
81.
Okay, 81 is the temperature. So let's find the volume.
45 or 40.
Which one? What's your starting temperature or volume? 45. See how easy that is? Don't make it hard when it's not hard. All right, Josh over here, this is the initial temperature, 81, but what do I gotta do? At the top, 2, add 273, hook me up. What you got? What you got? Just talk it out. I think you went the wrong way. You're saying 81 plus 273. I get it, T-Bone. $352? 4? I go the wrong way? Yeah, 354, my bad. Am I good? Okay. All right. Derek, can you give me a P2? New pressure? 50. Mr. Stein, can you give me a V2? 40. Rock and roll. And am I going to ask anybody for a T2?
No.
Why?
This is 273.
Because no, it's not 273.
You're looking for it.
That's what I'm looking for. Okay.
Oops, I'm done.
Like I said, it's just a matter of mathing it up. If you want to do it my way, 354 times 50 times 40. Divided by 120 times 45. Vote for 131.1, but let's let everybody else see if we agree.
Oh, so now that I'm pressing you, you want me to slow down?
All right, be cool, be cool. No. Look, just because you hear the answer, this is something that always hit. You gotta convince folks when they're doing work, because this is why the math book a lot of times will have the answer in the back. Okay, just knowing the answer don't help you. You gotta know how you get to it. So actually saying the answer doesn't hurt anybody, because I want to see that answer on your screen too.
I got 131.1.
That's what she said. Any problems? Any problems? Okay, 131.1 what, Ashley? Kelvin, good job. Now, this question doesn't say anything. It just says what, oh no, actually it does say. It says, what is the final temperature in Celsius? What do we got to do?
Let's subtract by 81.
You got to subtract 273 from 131. Where'd you get 81 from, boss?
Those are 40. Those are temperature, right?
That was the initial. I don't care about the initial. The initial, that's done. Not 142.
141.9.
Not 141.9.
One.
I got negative 141.9.
That is very different from just 141.9. I'm sorry, would you rather have $141 or negative $141? You with me? No, I feel you, but I'm just saying the negative sign is super important. Am I good? All right. Questions on that one? We'll do number 2, and then I'll set you free. Everybody feeling good? All right, starting over here on this side, so y'all be ready. All right. Sample of nitrogen goes from 21 meters cubed to 14 meters cubed. As pressure increases from 100 kilopascals to 150 kilopascals, final temperature is 300. What is the initial temperature in Kelvin? All right. Matthew, give me my starting pressure, P1. P1, starting pressure. Rock and roll. Josh over here, give me my starting volume. 21. And it doesn't matter what the unit is, as long as the unit stayed the same. If the unit changed, then you got to change it to match. But since most of these questions, they're going to keep them the same for us. Martin, starting temperature. You got number 2 up, Martin? You're not with us. Not with us. Mr. Styron, starting temperature.
T1,
Okay, why?
because you're looking for it.
Because you don't know it. Very good. Since that was a cop out, Mr. Styron, give me my P2.
150.
Perfect. Ashley, give my B2. 15, 14. And then anybody on the left, I don't care who it is, give me my starting, my ending temperature. Nah, I like your thinking, but you don't need to add 273. Why? Because it's already K. What do I want to put in here? K, Kelvin. Just take what they give you. It's just a matter of mathing it up. I like cross multiplying and dividing. You can do it however you want to those. I would say 100 times 21 times 300 divided by 150 times 14. Always put what you're looking for on the bottom. Always put what you're looking for on the bottom. So like I said, you cross multiply, the top is that cross, and your bottom is this cross.
Just 300 on the dot.
How's that possible?
I got 300 points.
I got 300 points.
Yeah, I got 300.
How's that possible, guys?
I don't know. You don't want to believe me?
Because what does that mean happened to my temperature?
It didn't change.
It didn't change. How's that possible?
It didn't get it.
It never changed. The initial was the final.
How? Because the pressure changed and the volume changed.
I have no clue. I didn't put time.
Look up there. Look up there. What do you see about the pressure and the volume that makes it so the temperature didn't change?
The V2 went down instead of
The volume went down and the pressure
went up.
went up. So since the volume went down and the pressure went up, it went up perfectly and down perfectly to keep my temperature the same. Make sense? Because if you think about it, you know if your pressure goes up, my pressure went up. So what do we expect temperature to do? Go up as well. But as my pressure went up, my volume went down, so that temperature was able to stay the same. Cool? Okay. Good job, guys. Keep on rolling. Pretty straightforward. If you get stuck and you need me, here I am. Let's go, let's go. If you're at home, thank you for watching the video. Have a great day. If you drink, don't drive.